Good afternoon, everyone. I welcome you all to this next lecture of Dynamics of Machine. And in this lecture, we will be discussing about the dynamometers. So, what is a dynamometer? A dynamometer is a mechanical device which is used to measure the power or torque output of an engine. All right. So, how much power or torque an engine is producing. So how we'll measure that? We'll measure that by the help of dynamometer. All right. So there are basically two types of dynamometers. First one is absorption type, and second one is the transmission type. So in the absorption type dynamometer, it actually absorbs the entire energy, that is the torque which is coming from the engine. It consumes that energy and converts it into the friction. Okay, so in that way, it is absorbing the energy. All right, and we will be using brakes. We will be a brake type mechanism will be used to measure the torque and power. All right. So in this absorption type dynamometer, the uh, power produced by the engine is absorbed by a friction resistance of the brake and is transformed into heat. All right. But the second type, the transmission dynamometer, in this energy is not wasted in form of heat, but it is used for some useful work while measuring the its power through the dynamometer. Okay. So transmission type dynamometers, the energy is not wasted in form of heat. It is transmitted through dynamometer to some other machine where the power is developed is suitably measured. All right. So these are the two types of dynamometers which we'll be studying. Okay. Fine. Now let's first go through absorption type dynamometers. So in absorption type dynamometers, we have to study this two types. That is Prony brake dynamometer and rope brake dynamometer. So let's go through this Prony brake. Now here you might be seeing this diagram. In this, let me make the explain the diagram to you. So over here you are seeing this small circle. Actually, this is the engine shaft. This is the shaft which is coming from the engine. Okay, and this is the pulley. Okay, which is mounted to the engine shaft with the help of key. Okay, so it is rigidly mounted. So the if the engine rotates, the shaft of engine rotates, this pulley will also rotate. All right. Now, uh, this pulley is surrounded by these two blocks, or we can say shoes uh, of the brake. Okay, it can be of any material, mostly wooden blocks are used. All right, so there is some gap between this pulley and the blocks. All right, now what our objective is to measure the torque or the power. So torque can be measured by with the help of while this pulley is rotating. Okay, so if we stop this pulley from rotation by bringing together these blocks with the help of this nut and springs, then what will happen? All the power or the torque that is being transmitted can be measured. All right. So over here, this is the lever, and this lever has free movement between these two stoppers S and S. All right. So this lever can move something like this. Okay, and it can move something like this. All right. So it is free to move. These stoppers are not so close, and they are actually a little bit far away from each other for this free movement of this lever. Okay. So on this end, we apply the load W. Okay, and in this end, there is a counterweight to keep this lever in the vertical position. All right. Radius of this pulley is R, and the frictional torque which will be produced will be denoted by F. All right. So when we turn on the engine, okay, these nuts and springs are there to give the movement to this lower block and upper block to move together towards each other and ultimately produce the braking effect to this pulley. All right. So now what we are going to do is we'll start the engine and this pulley will be rotating freely between these blocks. Now gradually we will tighten these nuts. Okay. Now I'm telling the procedure that we'll start the engine. So this pulley will also rotate. Now what we are going to do is we want to measure the torque. So we will start tightening these nut. Okay, as we tighten these nut, these blocks will start moving towards each other. And once they come in contact with this pulley, what will happen? Because of this friction, this lever will try to move something like this. Okay, all right, so lever will try to move something like this. Now what we are going to do is, as you can see, there is a load W over here. So we will apply more load. We will put more amount of load, and that will be put until this lever is again comes into the vertical position. All right. So this load, while in equilibrium, the torque which is produced, that is F into R, right? This amount of torque will be produced F into R, and while in equilibrium, this torque will be equals to the moment which is produced by this weight at the length L, that is about the center of the pulley. So it will be equals to W into L. Okay, so in equilibrium, this condition will be prevailed. All right, so we can measure at different RPMs also. So this is what we are going to do. This is how we are going to perform the experiment. Okay, so the same thing is written over here in the text. You can read it for your reference. So capital W is the weight of the outer end of the lever in newtons. So here is the capital W. L is the horizontal distance of the weight W from the center of pulley. As you can see, this is distance L from the center of the driving shaft or the engine shaft to the weight W. Capital F is the friction resistance between the blocks and the pulley in the Newton. As you can see, capital F is given over here. R is the radius of pulley in meters. This is also shown. N is the speed in RPM. Okay. So as I told you, this equation, that torque will be equals to F into R, this force multiplied by this radius, right? Frictional torque would be this, and in equilibrium, it will be equals to W into L. That is moment produced by this W about the center of the shaft. Okay. Now, once we have this value, we can measure the torque. Torque is power. Power in one revolution. What is, work done? Work done is force or torque multiplied by displacement. Okay, and displacement, what is the displacement? This is the angular displacement, and angular displacement is 2 pi. Okay, and 2 pi is the angular displacement in one rotation of this pulley. Okay, and if we want to calculate work done per minute, then we will multiply with the speed in RPM. So we will get work done. And brake power, that's why it is called brake power, because we are measuring it through the brake. So brake power will be work done per minute upon 60, that is 2 pi nt by 60. Okay, so ultimately the formula comes as power is equals to 2 pi nt divided by 60. Only the formula for the torque will keep changing as per the uh, machine. All right. So I hope this is clear to you how the Prony brake dynamometer works. Now let's move forward to rope brake dynamometer. See, the only thing in this dynamometer is if you understand the diagram clearly or the working clearly, then you will be able to determine the torque, or you will be able to deduce the equation which will be helpful for determining the torque and ultimately the power. All right. Now, as you can see, this is diagram of rope brake dynamometer. All right. So over here, let me break this down for you. This is the engine shaft or the driving shaft. Okay. And above this driving shaft, the pulley is mounted. All right. So this is the diameter of the pulley or the wheel, whatever you can say. Now over this wheel, uh, these are the ropes. Okay, and since the shaft will rotate, so this wheel or pulley will rotate, and to stopping the slippage of the pulley over the wheel, stopping the slippage of this rope over the wheel, we have provided this wooden blocks. All right. So as to produce a firm grip over the wheel or the pulley. All right. Capital D is the diameter of the capital D is the diameter of the wheel in meters, and small d is the diameter of the rope. So if you see the cross section of the rope, it will look something like this, and its diameter will be small d. So this is the wheel, and this pulley, this rope is one end it is attached to this dead weight, okay, where we will be keeping the weights for equilibrium, and this second end is attached to the spring balance. All right, so that spring will also provide some resistance. Okay, now what we are going to do is, initially there is no weight over here and we will turn on the engine. Now when the engine rotates, this wheel or pulley will also rotate. Now what we'll do is, gradually we will start increasing the weight over here. So the grip over the pulley will start tightening. All right, so what will happen, after some time, when this dead weight is of enough quantity, this will stop the this pulley from rotating. Okay, this belt will, or this rope will stop the pulley from rotating. All right, so in that case we will be taking the measurements, that is what is the reading in the spring balance and what is the amount of dead weight we have applied to, in order to stop that pulley from rotating. All right, so this is how it is working. Now there is cooling water has been supplied, because when this wheel or the pulley will be rotating within this ropes, a lot of heat will be generated. Okay, so in order to take that heat out, we have to supply this cooling water continuously. All right, so what will be the net load coming on the brake? That is W minus S, that is this weight, the weight, all that weight we have put, minus the resistance provided by the spring balance. Okay, and what is the distance moved in one revolution? So we know that distance moved in one revolution is equals to the circumference, and circumference is pi multiplied by d. But here the diameter of this rope is also be taken into account. All right, so its distance moved in one revolution will be pi into d plus d. All right, and now after calculating this, we'll be able to calculate the brake power. And again, brake power will be work done per minute. So work done is force multiplied by displacement. So this is amount of force. W minus S is the net amount of force, net load on the brake. Okay, and the distance is pi into d plus d. So this is the amount of work done in newtons divided by 60. Okay, so this is the brake power of the engine. Okay, and if we neglect the diameter of the rope, then it will become this force W minus S multiplied by this pi dn divided by 60 in watts. Okay, this n is the number of revolutions per minute, that is in rpm. All right, so this is how this rope brake dynamometer works. So I hope this is clear to you. Also this cross section is shown over here, that this is the part of the wheel section of the wheel rim, and from this wooden block is attached to it, and the ropes are passing this way. So maybe 2 or 3 turns of the rope can be used for getting a proper grip. All right, so these are the two types of dynamometers, which are absorption type dynamometers. Now let's move forward to the transmission type dynamometer. Okay, so there are 3 types. First is epicyclic train, second is belt transmission, and third is torsion. Okay, so let's see them one by one. Let's start with epicyclic train dynamometer. So epicyclic gear, you already know that in an epicyclic gear train, there is one sun gear. Okay, then there is one planet gear, and there is one annular gear. Okay, actually this should be something like this. Okay, so this annulus gear have internal teeth, this sun gear have external teeth, and this planet gear also has external teeth. Okay, so if this rotates in clockwise direction, sun rotates in clockwise direction, then this uh, planet gear will rotate in anti-clockwise, and this annulus gear will also rotate in anti-clockwise direction. Okay, so this is a typical epicyclic gear train. Similar thing is used over here. Okay, so the sun gear is also called as spur gear, and this planet gear is also called as pinion gear. Okay, and this outside gear is, as usual name, spur annular gear. So let me explain you the working of this. So the engine shaft or the driving shaft is over here, and this spur gear. or the sun gear is rigidly mounted on this driving shaft. Okay, it is keyed on the driving shaft. All right. Now, when this will rotate, let's say it is rotating in anti-clockwise direction. So what will happen to pinion? Pinion will rotate in clockwise direction, and hence this annular gear will also rotate in the clockwise direction. Okay. Now again, we have this lever over here, and this pinion gear is pinned on the lever. Okay, so it is free to move. So if the it is free to move like this, and there are stoppers so as to restrict its movement. All right. So we will be putting some amount of weight over here, and also this weight W counterweight is also over here to balance the this lever. All right. Now this distance between the center of the shaft and the center of the pinion, this distance is A. Okay, and this load W and the center of the shaft are L distance apart from each other. All right. Now, what will be the amount of torque that would be coming? That we have to measure by the help of this. So, when the engine shaft is rotating, let's say in anti-clockwise, so this spur gear will also rotate in clockwise. Now, what it will do, since this spur is rotating clockwise, so this pinion will rotate in anti-clockwise direction. So, the tangential force which would be coming, which would try to turn this pinion in clockwise direction, will be P. Okay. Now, in turn, this pinion will try to rotate this annular gear. Okay, and also it will try to climb over here. It will try to come over here. Okay. So, in order to stop that, because this annular gear will be connected to the output shaft, which will be going inside in another machine. Okay, in order to drive it. Okay. So it will since it has because of inertia it is not rotating in the initial movements, so this pinion gear will try to climb over here. Okay, so this lever will go something like this, right? So while this is happening, what we'll do is we want to bring lever back into this horizontal position. So we will start adding weight over here. Okay, and when we'll keep adding weight until this lever is back into its horizontal position. So uh, the total amount of force which would be this W would be providing is this load W, and the moment it is producing is this W multiplied by this distance L. So in equilibrium, this W into L, okay, this would be equals to this amount of force. So total force coming on the pinion will be one from the spur gear side and other from the annular gear side, and both will be in the same direction, and magnitude will also be the same. So the total force acting would be 2p, and this 2p is 2p amount of force is acting at a distance a from this center of the shaft. Okay, so this would be equals to 2 into p multiplied by a. Okay, so during equilibrium, this will be the condition. Okay, so now how we will calculate the torque? That torque calculation is also very easy. So this for equilibrium, as I told you, this 2p multiplied by a is equals to w into L. So we will get p is equals to w into L upon 2a. Okay, now this R would be pitch circle radius of the spur gear. What is this R? Pitch circle radius of this spur gear. Okay, and n is the speed of the engine shaft in RPM. And we also know that torque will be equals to this P, this load, sorry, this load P multiplied by this pitch circle radius. Okay, so that would be the amount of torque. And once we have this P value from this formula, we can calculate the power transmitted by this simple formula, that is 2 pi nt by 60. Let's substitute the value of T is equals to P into R. Okay, so this P can be calculated with the help of this arrangement. All right, and by subsequent calculations, we will find out the power and torque. Okay, so I hope this is clear to you. I'm not going through this text because whatever I'm explaining to you, it is same thing is written over here. Okay, so you can refer it for, later for your reading purpose. All right. Now the next type is belt transmission dynamometer. Okay, this belt type transmission type dynamometer has two extra names. They are also called as Froude or Throneycroft transmission dynamometer. Okay, so it has two extra names. Now, again in this there are four pulleys. This is pulley A, this is B, C, and D. So these are the four pulleys. All right, and the pulley A is mounted on the driving shaft. So here is the driving shaft. Therefore, this is called as driving pulley. Okay, and this is the driven pulley. From here, the another shaft may be this pulley may be mounted on the another shaft, which is connected to another machine, which would be getting the power from this driving pulley. All right. So what will happen? Let's say it is rotating in anti-clockwise direction. So when this is rotating in anti-clockwise direction, this two pulleys, this C and D pulleys are the intermediate pulleys. So there is a single belt which is going through all these pulleys. All right. So let's say it is rotating in anti-clockwise direction. So what will happen? There will be a tension T1 over here, which will be acting in this direction. All right. So the total tension acting on this pulley would be 2 times T1. Okay. Now it will rotate this pulley, and over here in this belt the tension would be T2, and here also the tension would be T2. So the total amount of tension would be 2 times T2. All right. So now what we are going to do is, since we already know that the tension T1 is always greater than T2, because this side of the belt is the tight side, and this side of the belt is the slack side. Okay, that is loose side. So obviously the tension T1 would be more than the T2. Okay, so now this is T arrangement. All right, and since the tension is more over here, this T arrangement will try to turn something like this. Okay, so now what we are going to do is we will again apply some weight over here until this comes back into its original position. All right, so that weight we will measure, and we will by measuring that weight we will try to calculate the amount of torque which is being produced. Now how we will calculate that, let's see. Okay, this T1, this 2 times T1. Okay, diagram is also here. So this 2 times T1, the total force as coming on this pulley C would be 2 times T1. And what will be the moment it will be producing about this fulcrum point E? It will be 2 times E1, 2 times T1 multiplied by this distance A. Okay, and also this 2 times T2 will be producing the moment, which will be equals to 2T2 multiplied by A. Okay, and also distance between these pulleys and this load W is the L. That is, this is the fulcrum point. E is the fulcrum point. Okay, so we'll be taking all the moments about that. So now taking moment about pivot E, then 2T1 into A. This will try to rotate the system in anti-clockwise direction, which will be equals to 2T2 into A. 2T2 into A about point E. It will try to rotate in clockwise direction, and again this load W will try to turn in the clockwise direction. So this will be plus W into L. Or from here we can determine this T1 minus T2 into W into L upon is equals to W into L upon 2A. Okay, so D is the diameter of pulley A. Capital D is the diameter of pulley A, and N is the speed of engine in RPM. So work done in one revolution will be 2 T1 minus T2 into, that is the this torque multiplied by the distance. What will be the distance traveled in one revolution? That will be pi into D. That is the circumference of this pulley. All right, and in 1 minute we'll multiply it by N. That is radians rotation per minute, RPM. Okay, so this will be the amount of work done, and this work done again uh, we can calculate, we can convert it in terms of power by T1 minus T2 into pi dn divided by 60. Okay, so this is how this belt transmission dynamometer works. Okay, so now we come to this last dynamometer, which is torsion dynamometer. Okay, so as you might have studied in strength of materials, the torsional equation, which was tau by r is equals to T by J into C theta by L. Okay, so we will be using only this part of the torsional equation. So T is the torque, J is the polar moment of inertia, this C is the modulus of rigidity, which is constant for a material. This theta is the angle of twist in radians, and L is the length of the shaft, okay, which is taken into consideration. Okay, so this J for solid shaft, this J is the quantity dependent on the cross section. It is sectional property. So for solid shaft, J will be pi by 32 d raised to power 4. For hollow shaft, it will be pi by 32 d raised to power 4 minus d raised to power 4. Okay, so from here we can see that T is equals to C into J upon I multiplied by theta. Okay, so these three things are constant. That C is also constant, J is also constant, and L is also constant. Only variable is this theta, and this theta is the angle of twist. So if somehow in some shaft we are able to determine the angle of twist, then we will be able to calculate the torque uh, transmitted by that shaft, and ultimately the power transmitted by that shaft. Now, how we will measure this angle of twist? Okay, so this angle of twist can be measured by experiment which is called Bevis-Gibson flash light torsion dynamometer. Okay, so in this, what these two scientists did was they mounted two plates on the shaft. Okay, and they made a one hole in both these plates. Okay, and those holes were aligned to each other such that if you pass a light from here, it will that light will totally pass from this hole. Okay, so these two holes are totally aligned with each other. Now, what they did is they attached this part of the shaft to the output machine, and this left end of the shaft to the engine. Okay, they attached this to the engine shaft. Now, as you already know, that when a shaft rotates, let's say this is the shaft, okay, and when it rotates, there is always some angle of twist, because by that only this power is transmitted. So if this end has rotated 30 degree, this end might have rotated 29.8 degree itself. Okay, so that much amount of twist, that much very small amount of twist is produced while the power is transmitted. Okay, so you might have already studied in strength of materials that how much amount of twist is allowable in a working shaft. All right, so now what they did is to measure this much amount, uh, as this part of the shaft will, this left part of the shaft will rotate more compared to this right part of the shaft. So what they did is they kept a light source over here. So this L is the light source, okay, and it will pass the light from the hole in plate A, and when the shaft is in straight position, in that case the light which is passing through hole A will totally pass through the hole B. Okay, now once there is a small amount of twist in the shaft, uh, that entire light which was passing through the light hole A will not pass through the hole B. Okay, so a small amount of light will be obstructed. Okay, so over here they kept a measuring plate, that is vernier. They kept a vernier plate over there. Okay, or that plate is also called as perforated plate. So it can be seen over here. This is a perforated type of plate. This is the side view of this E. Okay. So this perforated plate, even it can measure up to 1/100th of a degree. Okay. So even if this shaft rotates by 0.01 degree, this plate will be able to measure that amount of twist. Okay, so uh, they will pass the light from here, and the small amount of light which is not passed, it will be measured with the help of this perforated plate. Okay, so by that measurement we can determine how much amount of twist is produced in this shaft while transmitting the power. And once we know that amount of twist, that is we can the angle by which that twist is produced, we'll put the value of that theta in radians over here and we'll calculate the torque. And once we have the value of torque, we will calculate the power, and that much amount of power is being transmitted by the shaft while doing its work. Okay, so I hope this is clear to you. I'll share these notes with you, and you can just go through this text, all these text. So whatever I explained is all written in text over here. Okay, so you can refer that for your revision purpose. All right. So I hope the topic today, which we discussed, that is the dynamometers. All the dynamometers, we actually discussed 5 type of dynamometers. Basically, it is divided into 2 types. That is absorption type and transmission type. So in type, we saw 2 types of dynamometers. One was Prony brake, and other one was the rope brake. Okay, and in transmission type dynamometer, we saw 3 types. That is epicyclic-train, belt transmission, and torsion dynamometer. All right. So I hope this is clear to you. So I'll end my class over here. Thank you everyone for joining. Have a good day.